Welcome, this is lecture 24 on central composite designs and response surface methods. This lecture will be recorded in three parts. Part 1 will be on central composite designs. Part 2 will be on the theoretical background for response surface methods. And Part 3 will be two examples of using response surface methods. The first of the two will be from the RSM package for R, and the second will be a paper from the literature. Here is a brief overview of what we'll do today. And just a reminder that this is a lecture for November 25th, which is recorded. If you have any questions, please post them in the appropriate place on the discussion board, and I hope that some of us, either myself or someone in the class, will be able to help you out. We'll meet again on December 2nd, where we'll continue with Taguchi designs. But let's begin with a review of the material covered last week. You see here two geometric examples of central composite designs. And when we use the term geometry in this context, we're talking about the spatial arrangement of experimental runs in the space that is defined by the factors. In the diagram on the left, you'll see two factors, x1, x2, that define a plane of experimental runs, and each of the experimental runs is a black dot, a circle that you see. If it is a 2 to the k design, then it's simply the four black dots that are the corners of the square that you see. And what makes this a central composite design are the additional 5 experimental runs, one that is at the center or the origin of the coordinate system, and the additional 4 circles that represent the 4 experiments that are located a square root of 2 distance along either of the two factor axes, and that's a plus the square root of 2 or minus the square root of 2. So a central composite design for 2 factors begins with the original 2 to the k design that is shown in the 4 intersections, and the additional 5 points, 4 along the axes, 1 at the center. On the right-hand side is a 2 to the 3 design, 3 factors, x1, x2, x3. Those 3 factors define a 3-dimensional factor space, and the 8 experiments are the corners of the cube. As I'll just illustrate one of those here, where the mouse pointer is a second and a third corner. In this case, you see an additional 7 experiments. 1 is at the center, pointed to with the mouse, and then there is 1 perpendicular to each of the 6 faces. Here's the first of the 2 along the x1 axis, the second of the 2 along the x1 factor axis, x2 minus x2, x3 minus x3. So there is an additional experimental run along perpendicular to each of the 6 faces, and an additional 1 at the 7. So there's 8 plus 7, or a total of 15 experiments in this case. Now, I referred to this earlier as a geometry, and I mean this in the broadest possible sense, a geometry referring to the spatial arrangement of objects or things. And for us in the design of experiments, the things that we're talking about are experimental runs. A collection of the experimental runs forms an experiment which can be depicted or shown in a geometry, as you saw on the previous slide. When we began the study of 2 to the k designs, we used these 2 to the k designs to determine main effects and 2-factor interactions, and we did that quite simply by drawing planes connecting some or all of the experimental runs. in this geometry. But with a simple 2 to the k design, we're limited to the kinds of surfaces that we can depict through this factor space. In order to depict a second order, a quadratic surface, one needs additional points. And you might remember this from your study of interpolation or extrapolation. And central composite designs are the most popular class of designs for fitting second order models. There are others, as you'll see later on in this course. We'll talk about several others, and even in this lecture. But central composite designs are the most popular. And a central composite design, as you saw in the previous slide, is composed of several parts. One begins with a 2 to the k fractional factorial design, which has n equal 2 to the k factorial experimental runs. There are 2 times k axial runs, as you saw in the 2-dimensional and 3-dimensional case. And then there are n center runs. And we need the additional n center runs to interpolate this second order model. So there are 3 parts. There's the original fractional factorial design, n equal 2 to the k, 2 times k axial runs, and n center runs. Now we show those graphically as just a single point in the center, but keep in mind that there are n needed in order to fit the second order model. Here's an example, once again, of the 2-dimensional factor space x1, x2. And we show the coordinates of the original fractional design using a normalized or dimensionless coordinate system, where they're located, as you see, at either this experimental run is shown with the assignment 1, 1 for the 2 factors, 1, -1, -1, -1, and -1, 1. Here are the axial runs, minus a square root of 2, 0, plus square root of 2, 0, and similarly along the x2 axis. And the n copies of 0, 0 are shown here at the origin. This figure, of course, was taken from Montgomery's text. This shows you the experimental design in 3 different parts, or the design matrix in 2 different parts, and then the response variables. The first part on the left are what is referred to in the picture as the natural variables, but these are the original factors and the values assigned to these factors, but in the original units of measure. They're shown as C1 and C2. And they are coded, though, in our geometry or geometric representation as variables, dimensionless variables, now x1 and x2, normalized to the scale -1 to 1 for the original fractional factorial assignments. So for the variable C1, which has the range 80 to 90, 80 is scaled to be a -1, as you see. Here's 80 and -1. 90 is the upper limit. That is scaled to be 1. 85, halfway in between, is the center. These are the center runs at 0, 0. Now, the same scale is not used for the second variable. It has its own scaled representation. It's 170 to 180, so it's -1 is 170, 1 is 180, 175 is the center. These are the center runs, and then these are the axial runs. So what you see here is in 3 parts: the original fractional design, the n copies of the center runs, and then the axial runs. For this particular experiment, there were 3 different response variables: the yield of a chemical process, the viscosity of the fluid, and the molecular weight of the material. And so the coded variables represent the design matrix, and this represents the complete data frame, including the design as well as the 3 response variables. Notice that the axial runs here at the bottom, of course, are at the coded values of square root of 2 or minus square root of 2, which then have to get translated back to the values of, in this case, 92.07, 175, or 77.93, 175. So central composite designs are techniques that are used if you have quantitative factors. You first take the natural or dimensioned variables, code them or scale them, if you will, to the dynamic range given. Then you construct the design matrix of 3 different parts, the last part having the axial values. So once again, these are the original diagram that you saw with the coordinates, and here alpha is representing the general case where we've been placing the axial runs at alpha equals the square root of 2. Now, this allows itself to a central composite design being used for sequential experimentation. And remember, this was one of the motivations for a fractional design. One could take a complete factorial design, construct 2 or more fractions, and run the fractions sequentially. In this case, if one had a central composite design, rather than a full factorial design, you first run the fractional part, the 2 to the k, fractional design, and fit a first order model. Then add the axial runs to fit the second order model. And one adds the axial runs and, of course, the duplicated center points to fit the second order model. So here you immediately, as a result of the central composite design, then have 2 models to compare. This is one way of exploring 2 or more models from the same experiment. The one choice that you have, of course, is the distance of the axial runs from the center. In the previous slide, they were represented simply as alpha. It's a choice one would make when constructing the design. In the examples that you saw earlier, we happened to select alpha to be the square root of 2. Now, that's somewhat arbitrary, except for the fact that the further apart you place those, the worse fit that you'll have to the second order surface. And you might remember that. Again, I would refer you back to prior study of interpolation and extrapolation. So the further apart you space those, the error in the fit of the surface is going to be proportional to the spacing between the points. Again, there are n copies of the center points, which you'll need to fit a second order surface. If you refer back to numerical methods where you're constructing numerical fits of second order surfaces, you'll see that that's where the center points are duplicated. Now let's think back to the idea that we are thinking about experiments as a collection of experimental runs in a factor space. So we're thinking again about geometry. And one way of evaluating a central composite design is by this geometry, or the spatial arrangement of the experiments. And one factor, or well, let me not use that word factor, but one criteria that one uses to evaluate an experimental design is rotatability. And what do I mean by rotatability is whether that spatial arrangement of experimental runs can be rotated through that space. So another way of thinking about this would be that if you changed the factor values to be linear combinations of the original factors, say x1 and x2 in our two-dimensional case, that would have the same effect as if you rotated the experiment through that, so that instead of the axial points being at square root of 2 comma 0, and you rotated the experiment, then the square root of 2, both of the coordinates would change. So if an experiment that is in a set of experimental runs is rotatable in a geometric sense, then we have reason to believe that we will get good predictions of the model of the response variables using this model throughout the region of interest. And a region of interest is that portion of the factor space in which we believe that the factors will take on values associated with the experiments. So in the example from Montgomery that I showed you earlier, if the dynamic range of the variable C1 was 80 to 90, and I rotated the experiment, then the values that x1 would take on would be within that range. If I get good predictions of the response variable from that second order model anywhere within that range as I rotate it, then the rotatability suggests that this is a model that is effective. It's a good model. It'll give me good predictions. Another way of thinking about rotatability would be that the variation in the response variable would be constant on a sphere. So this is not a two-dimensional case now, but if I have a three-dimensional space or something higher, that is, there's three or more factors in this experimental design, then the response values lie on a sphere or a higher dimensional surface, and no matter how I rotate that experimental design or how I change the assignments of the factors so that the position of the experimental runs change, if the variation in the response variable remains the same, then the experiment is rotatable. And then I have confidence that this experiment will give me good predictions. The model that's suggested by this experiment will give me good predictions. You can form contours or lines, through this space of the predicted response. It'll turn out that these are concentric circles, and you'll see where that's used in just a few minutes as a diagnostic tool, much in the same way that we had other tools for model adequacy checking. Here's a geometric representation that one uses to evaluate central composite designs, and simply take the word for it now that you can form contours or level sets where the standard deviations representing the variation in the response variables, and if you form contours of constant standard deviation, they'll form concentric circles. So again, that the rotatability in a geometric sense, the rotatability of the experiment, of the set of experimental runs, is intimately tied with the variation in the response variable. So that an experiment that's rotatable will give you good predictions of the response variable, and you can evaluate that by examining contours of constant variation. And this is what one can use to evaluate or to select a response surface design. Now, this is a very general approach we're talking about, that the design has three parts. You start with part A, a fractional basis. You add center points, and then you add axial points. Right? And the number of center points and the number of axial points will depend on the size of the fractional design and the order of the surface. Presumably, we're interested in a second order model or higher. And the basis on which we'll choose the model will be the rotatability in its geometric sense. If you have 3 dimensions or higher, we're talking about spherical central composite designs. And if it's a spherical design, that means that all the original factorial runs and the axial runs are on the surface of a sphere. Now, we didn't do that in the 2 examples that you've seen. The axial runs were further off the faces of the cube. So that's central composite design, but it's not a spherical central composite design. Right? So the value alpha that one chooses will dictate whether it's spherical or not. In fact, you could make it further out than the square root of 2, but if you brought those inwards, then you could place all of those axial runs on a sphere along with the original fractional factorial runs. Okay, now let's talk a little bit about the center runs. If you have a spherical center composite design, you must have somewhere between 3 to 5 center runs to stabilize the variance. Now, I've talked about the number of center runs in the context of fitting the second order surface, and that in fact is true. But remember that one includes a n, center runs, so that this number of center runs is on the order of the number of fractional factorial points. So if you have a 1/2 fraction of a 3-factor design, it's on the order of 4. So you'll have somewhere between 3 and 5. If you follow the original algorithm or prescription, if you will, you would include 4 center runs. So it has the effect of giving you the numerical stability you need to interpolate the second order surface. But if you think about it in terms of the variation of the response surface, it'll give you sufficient stability in the response variable. There's one variation of a central composite design that's called the Box-Bankin designs. And Box-Bankin designs are 3-level designs for fitting response surfaces. A central composite design is much in the same way. We're adding additional levels by interpolating. We're adding axial runs that give you additional levels. You can think about starting with 2 levels and you add a 3rd level that's one of the axial runs. Right? So Box-Bankin are a variation of this addition of axial runs to a fractional design. But rather than starting with fraction and adding a complete set of axial runs, you start with a fractional design and you add to that an incomplete block design. So we'll show you an example in just a second. The advantage of a Box-Bankin design is that it has fewer experimental runs than the central composite design, but it does preserve the rotatability, or truth be told, it's nearly rotatable. Okay. So these are spherical designs. All of the experimental runs lie on a sphere in this geometry of the factor space, and so you can imagine in your mind's eye that the sphere being rotatable geometrically would suggest that your experiment is rotatable, and it would give you a method for fitting response surfaces that are both efficient but predictive as well. Box-Bankin designs do not contain points at the vertices of cubes. These are spheres, remember. So it's not one of the first two factors that you saw, or the three-dimensional factor example that I showed you in the beginning of this part of the lecture. Okay, so we started with central composite designs, talked a little bit about box-Bankin designs, which start with a fractional factorial and you add an incomplete block to that. The third variation of this is called a face-centered central composite design. So, as you might imagine from the title, that unlike the spherical central composite design, or unlike the box-Bankin design, which is spherical, a face-centered design has a region of interest that is the cube, if it's 3 dimensions, rather than the sphere in the 3-dimensional factor space. That the additional points, the axial points, are on the faces of the cube. The advantage is it requires only 3 levels. So you don't have points that are outside. You don't have points at minus the square root of 2 or plus the square root of 2 along the axes. They simply lie on the faces. So rather than having 4 levels of the quantitative factors, if you have a face-centered design, it requires only 3 levels of the quantitative factors. So you only need to interpolate values of the quantitative factors. You don't need to extrapolate beyond the regions that you believe to be the limits. All right, so these are not rotatable. As you imagine, if you took a cube and tried to rotate in space, you don't get a symmetrical object. With a sphere, when you rotate it, you do have that symmetry. Face-centered central composite designs are not rotatable for that reason. Okay? But because of the way it's constructed, you don't need as many center points as the spherical. Remember, we needed 3 to 5 in a spherical, with 4 being typical for the 1/2 fraction. Here you can get away with only 2 or 3. Because you have a built-in redundancy when you're trying to fit the 2-dimensional or the quadratic model. If you do add more, and then you can separate the instances of the center runs in fitting the surface in either of the 2 or the 3 dimensions. Then you can actually get a better estimate of the experimental error. And again, without belaboring the point, if you refer back to numerical methods and fitting a quadratic surface, you can get different estimates of the goodness of fit by locating the origin either at one end or in the center, and that the order of the error will change as a result. So the more center runs you have will allow you to change the actual numerical model you'll use to fit the surface, and changes the error as a result. Simply put, without delving into the theory, more center runs will give you a better estimate of the error. So let's take one step back. Here is a 3-variable box-Bankin design, 3 factors, and there are, as you see, 15 runs. In this case, you see that the center runs are 13, 14, and 15, right? And the axial runs, you don't see here, right? Because this is a spherical design. And what you're looking at, although you might think, well, gee, this is, this looks like a cube because I have say, these coordinates at the extremity and x3, at the center, and it looks like a cube, that you can fit a sphere through each of these points, and then you add the center points. Okay, so here's the box-spanking design that we were just looking at. Here's the center points. Here are the points on the faces, and you see the scaled variables -1 to 1, -1 to 1, -1 to 1, and see the nature of this being an incomplete block design because I don't have the original runs at the corner. Right, so this was the box-spanking design. Here is a face-centered design for the same three factors, or the three-dimensional factor space. Here's, you see, the original experiments from the fractional factorial design that I'm highlighting with the mouse. And the additional experiments form what's referred to as a star, where these points that I'm highlighting with the mouse now are actually on the faces. So this top face has the 4 corner points of the original fractional design, and an additional point that's the center of the face. Here's the center of the cube. Face-center design for k equals 3 factors. The box-spanking rotatable design for 3 factors. Okay, this one's rotatable or nearly rotatable. This one is not, right? And you can see, because you can fit a sphere through these points. You don't have the corner points of the fractional design. This one, the face-center design, is not rotatable.